All right. Hello, everyone. Welcome to, I think, week 6 of network science. I'm going to be talking about random network models today, and I'm going to share my screen with you quickly. And so before I even begin talking about random network models, I want to note that really what we're going to be talking about today would cover somewhere like 5 weeks in a graduate level network science course. And so I am only going to really introduce you to topics. I am not going to kind of teach you the whole thing. But I do want to point you towards where you can learn a lot more about these topics. So if you go to the network science wiki page on BVCN, you scroll all the way down to the bottom. There's this SFI graduate course on NetSci. And so the Santa Fe Institute is a big complexity science institute. They have some great coursework that's online and free. If you look at their Complexity Explorer, they'll teach you all about complexity science, of which network science is kind of a part. They also have summer graduate courses that are really fun, and I highly recommend. If you want to check out this specific course, will it let me? There we go. This is taught by Aaron Clauset, who is, I think, at University of Colorado Boulder, but I might be wrong. In any case, this is a really nice course. I took his kind of shorter version of this course at SFI, and he has lecture notes that you can download. And I think these are really great for, I mean, he says that a prereq for the course is a relatively strong math and stats background. And I think that's maybe true if you want to do the homeworks that are associated with these lecture notes, but I think the lecture notes themselves are extremely clear and really try to give you intuition about what's going on. And so I would highly recommend reading through them, especially starting at lecture 3, where they start with random graph models, which is what I'll talk about today. But also that continues into lecture 4 and lecture 5 and lecture 6, and there's a lot of what we'll be talking about today. So I'm covering broad but not deeply with most of this stuff. Get to that in a second. So I'm going to stop sharing or new share. Hopefully this works. Share. Joy and Jacob, can you give me a thumbs up if you see a thing that's untitled? Good? Okay, great. So I just want to talk to you a little bit about why we're talking about random network models and what random network models are. So a lot of questions have come up about, what is the relevant structure of my network? How do I look for structure in my network? What does that even mean? And a useful way of kind of dissecting the structure of your network is to compare it against a random model and see kind of how your realized network, your actual data network, is different from kind of this randomly drawn network. And when I say random, oftentimes people think that kind of means uniformly distributed. I'm really talking about kind of stochastic network models. So there's different processes that can lead to different distributions, right? But there's some randomness in that process that generates the network. And so you might have a network that is truly kind of uniform, and that's the Erdős-Rényi network, is this network we're seeing right here, where basically we have a bunch of nodes, and we're going to say these nodes will be connected with a probability p, and we'll draw a number between 0 and 1 for each pair of nodes in the network. And if it's above that p, we'll, or I guess it would be below that p, we will add that edge to the network. And that's kind of the simplest generative network model you can have, where you say, everything happens kind of with equal probability. You can constrain the Erdős-Rényi network to have more similar features to your network. If you want to constrain it to have the same degree distribution as your network, or at least the same average degree as your network, that's possible. You can constrain nodes to have the same exact degree. There's all sorts of tweaks to this model that will generate slightly different networks if you want to control for different factors in your own network. There's also networks that look totally different from this, right? So this is a network that you might have seen something like this in your own data. It has a lot of kind of really densely connected hubs, right, that have lots of connections, and then a lot of nodes that really don't have very many connections at all, right? So you have um, kind of some highly connected nodes and some kind of weakly connected nodes. And this is produced by the Barabasi-Albert network model, which we'll talk about in the actual lesson or tutorial. But basically, this is a rich gets richer type model of how this network is generated, where you're going to add nodes to the network iteratively, and each time those nodes are added, they're going to get connected to things proportional to the probability of the degree they already have. So if a node has a high degree, it's more likely to get new connections, and it kind of accumulates many connections. Whereas if a node has low degree, it doesn't get to accumulate those connections. So there's lots of different types of networks that you might expect to follow that sort of generative process, right? And that's going to produce a very kind of characteristic structure. And then something we've talked about a lot is modularity, right? Or kind of looking for neighborhoods in your network. And so thinking about what sort of generative model will produce neighborhoods in a random network. So I'll talk at the end of the tutorial briefly about stochastic block models. And these are basically an extension to that very first random network we saw, which is called the Erdős-Rényi network, where you have kind of two kind of very simple random networks that are connected with different p's, and then you connect them also with some probability p. So you specify a probability matrix, you've already specified the number of clusters you want in this network, and then you can generate that network. And I'll show you how to do that. The nice thing about this is that it gives you kind of you have this generative model of modularity or of kind of neighborhoods in your network. And so you can actually try to fit that model to your network as a way to detect neighborhoods. And it gives you kind of a statistically rigorous way to do that. So a lot of times we'll think about kind of what sort of model produces that behavior structure, right? So we've talked about kind of three very different structures today. We've talked about kind of this like flat network that doesn't really have any interesting structure. We've talked about network hubs and how you might get to network hubs. And then we talked a little about communities and networks and how you might get there. And there's different types of models that will lead to each of these. And so then the question becomes, how do we compare our data to these networks, right? How do we say, okay, our network kind of looks like this generative process or this other generative process? And we've actually already covered a lot of the ways you do that by looking at all these network statistics that may have seemed kind of, we got a lot of questions about, yeah, but like, what does this network statistic mean? And it quantifies some structure in your network, and it's not actually, the statistic alone doesn't tell you so much, right? Like the mean of a distribution tells you something, but you really get interesting results in science when you compare means, you compare variances, or you compare medians, right? Without context, those statistics don't mean anything to you. And similarly, that's true of the network statistics we've talked about in the course so far. And so just to give you an example, if we look at the degree distribution of that gut network we looked at the other day when we were building our speakeasy network, the dots here are degrees. So K is degree, and this is the probability of degree across the network. So this is basically describing the probability that a node has a particular degree in that network. And I've noticed I've log scaled the x-axis, which is a pretty common thing to do. You'll see that this degree distribution looks roughly linear. That corresponds to what people might call a power law distribution, although I doubt there's sufficient data here actually to make that claim. And I'll send you, there's a link in the lesson to kind of a more rigorous R package that will let you test that sort of hypothesis in your own data. But what we can say is that this is probably not an Erdős-Rényi network, because if it was, the dots would follow this black line here, right? And so we can see that our network qualitatively, the degree distribution does not look like an Erdős-Rényi network. And you wouldn't necessarily expect a species interaction network to have this kind of extremely flat, random, featureless, sort of structure, but there's one way of kind of rigorously looking at that, and we're going to take you through kind of a bunch of ways to rigorously look at that in the lesson. So, new share. Let's go to Chrome again. And so, when you actually get to the lesson, it's quite a bit longer than this. There's a lot of text this week because I do want this to kind of send. You should read the text in the lesson. It repeats a lot of the things I said here, but maybe with a little bit more thoughtfully. So we're going to go through Erdos Rainy networks. There are some missing accents that I need to put in on Erdos and Rainy. So I'll show you actually the code to generate these networks, which is really easy to do in igraph. We'll talk about some features of how these networks can change when you change parameters. So a small parameter change can lead you from getting this very sparse network to this totally connected network, which is pretty cool. We'll look at these degree distributions quite a bit. It's kind of the simplest way to look at your network structure. So this is kind of what the distribution of the degree distribution of the Erdos Rainy network looks like. And then you can actually fit a theoretical distribution of what you expect there. And so it's a good fit. We'll talk about this Barabasi-Albert model, how you generate that. Again, very easy. Again, you're going to get a very distinctive linear. So this is the Barabasi-Albert model, but it looks a lot like that gut profile we saw just now. And again, we see that the expectation from the Erdos Rainy random network is not fitting very well. I'll show you how to generate stochastic block models. Then I'll also kind of, here, they have weird degree distributions, and then finally, I'll show you how to use stochastic block models. You fit them to your data, and you can do community detection using them, right? So this is refitting that model and trying to get the community back out. And then I think as a bonus, I think you should play around with that Speakeasy network or some of the other networks we built in the course, or your own networks, and try to at least look at the degree distribution, see what the shape of the degree distribution is, and say, does it look like a random network? And by random network, I mean, does it look like an Erdos Rainy network? Does it look like it has this kind of linear, what we would call a scale-free property? So this is often called scale-free because you have some nodes with really, really high degree and some nodes with really, really low degree. And essentially this distribution has infinite variance. And so there's no one scale that you can look at the network on that is relevant. You're talking about degree. And so does your network have that property? I think it's worth at this point, and I think most people in the course are already doing this, just playing with data to try to get some of these methods to work on your own data. And that's it for today.